Hey everyone, welcome back to the channel. I want to talk about trade-offs in system design. This is the first video where I'm talking about several concepts in system design, and every video will increase in complexity until we talk about how we design several complex systems in the world. I'll focus on performance and scalability, latency, and throughput, and the CAP theorem in this video. If a service has two resources and then you increase the two resources to about 3 resources, or maybe 4 resources, or maybe 5 resources. If the increase from 2 resources to 3 or 4 or 5 resources results in an increased performance, then we say the system or the service is scalable. Increasing performance means your service or system can now serve more units of work or larger units of work, like larger datasets. When your system is slow for a single user, then you have a performance problem. If your system is very fast for a single user but is slow under heavy load, then you have a scalability problem. When you have an e-commerce page that is responsible for giving you a list of products that you have to buy, and it takes about a number of milliseconds, let's say approximately 500 milliseconds for you to see the product list. And then you also click on a particular product to be able to see the details of this particular product. And let's say it takes you approximately 100 milliseconds. This time, that is the 500 milliseconds and 100 milliseconds, is referred to as latency. Latency is the amount of time it takes for you to perform some action, and also is the amount of time it takes to produce some result. If this e-commerce site can only produce about 50 listings per day, let's say maybe 20 hours. A day might be too vague, I'll say 20 hours. And it can show approximately, let's say 50 or 60 detail pages in probably an hour. The 60 and 50 can be known as the throughput. So throughput is simply the number of those actions a system can provide in a particular time, or it is the number or quantity of results that a system can provide in a particular time. So usually the goal is to aim for the maximal throughput and acceptable latency. Let us talk about the CAP theorem. CAP is an abbreviation, and C stands for consistency, A stands for availability, and P stands for partition tolerance. CAP theorem applies to distributed systems. A distributed system is simply a collection of nodes which have been networked, and these communicate and share data. But to a user, they appear as a single coherent system. What is C, A, and P? The C, like I said, stands for consistency. It simply means that when a read operation happens, every read or that read operation must get the most recent write. Meaning all the nodes in that distributed system must see and have access to the same data, and that data must be the most recent written data. It must always be accurate, and that gives us consistency. That is what the C stands for. Then the A means that when we have a request that has been sent to the system, we must always give a response no matter what. But this means that some responses can have stale data or old data. The data will not always be accurate. It won't be the most recent write given to you. Then we have the P. The P, like I told you, stands for partition tolerance. In a distributed system, it's inevitable that you'll have a network partition. A network partition simply means that your nodes at some time can have a network failure, and they can fail to communicate for one reason or another. You may not even know why until you investigate. When a network failure is going to happen, you can't tell that. That's why I said it is inevitable that we shall have a network partition or a network failure. It is called a network partition because some nodes become isolated, okay, because of network failures. Now, in CAP theorem, because we know that network failures are inevitable, we must design systems which are partition tolerant. That's why the P stands for partition tolerance, meaning that even when the network has an issue or we have a network partition, we must have our system operating. The system must operate even when there is a network failure. We must have a way of handling that. Because we know that network partitions are inevitable, it leaves us with only having to decide between consistency and availability. And because of that, the CAP theorem says, since, like I've just mentioned, we have issues concerning the networks and they're inevitable, they are going to happen, we need to consider only consistency and partition tolerance, or availability and partition tolerance. Theoretically, you can achieve consistency and availability, but in a distributed system, it is practically impossible because network partitions are inevitable. They happen. So our focus should be on CP and AP. Now let's talk about CP. The CP simply means that when a request is made, and this request, for example, is for a read operation, we must always provide consistent data. We must always provide the most recent write. In the event that there is a network partition, we can either return a timeout error or any other type of error. So with CP or with consistency and partition tolerance, we should either give the user or the client the most recent accurate written data or an error, which could be a timeout error. Then let's move on to the next one, which is the A and the P. A for availability and P for partition tolerance. This means that when a request is made, we should always give the client something. We should always give them a response, even if it means that the response could be stale or old data. The point here is that give a response no matter what. Do not give an error. And of course, like you know, it does not guarantee that you'll get the most recent data. Have that at the back of your mind and you'll be able to design systems better. Now, I've just touched the surface on this, and as we go deeper in other videos, I'll touch on this again and again. If you have any question, please leave the question in the comment section. I can create follow-up videos to give examples or build on top of this. Also, if you're enjoying this series, please like the video and I'll see you in the next video. Please let me know in the comment section if you're enjoying this series.